Hello calculus students, here we are with continuity and one-sided limits. We're going to take on a few things here. We've looked at discontinuities before, and now we're just going to see how to describe continuity and give a more formal definition to it. Basically, it's this idea that a function's continuous if you can draw it with a continual line. And so right here we see a problem. That little hole there is a discontinuity. Same thing over here. We try to draw this without losing our pen, not picking our pen, but we're going to have to pick it up to jump down to here. So here's another example of a discontinuity. The function's defined there, but the limit doesn't exist because the directional limits don't agree. As we come from the left, it goes up to here. As we come from the right, it comes down to here. And here's an example where the function exists and the limit exists, because it looks like the function is getting closer and closer to this level from both directions. But the limit of the function and the value of the function don't agree. So we also call this discontinuous here. So this gives some examples of what creates something that's not continuous. Either the function is not defined, or two here, the function doesn't exist, the limit does not exist, as we saw in this example, or the limit and the value of the function don't equal each other. So, if you don't have any of these discontinuities, then basically it's called continuous. And here's our definition of continuity. The function's got to be defined. The limit, as x approaches z, has to exist. That means the directional limits agree. We'll talk about directional limits in a second. And this limit must equal the value of the function. Okay? Now, here's a few exploration problems. And we're going to try and describe when the following functions are continuous over this interval. So here in our first one, x squared plus 1, just a happy parabola raised up 1. And from negative 3 to 3, everything seems fine. It's a parabola, and basically a polynomial function is everywhere continuous. That's because we restrict our powers to whole numbers. So there's no division by 0 possible or square roots of negatives. So this is defined everywhere, it's everywhere continuous, and we've got no problems from negative 3 to 3. Our next one, 1 over x minus 2, getting into the rational functions now, where we saw some problems in the past. And sure enough, at 2 we've got a vertical asymptote. So this one is everywhere continuous except at 2. So it's only continuous from negative 3 to 2, and then from 2 to 3 when we're restricted to this interval. And C, it looks fine, and when you put in your graphing calculator, you'll probably see it just looks like a straight line, because this reduces down to x minus 2. The thing is, though, you get that hole at negative 2. And when I actually did C, I put a point in here and traced it, it disappeared at negative 2. And I think you'll find that too if you trace it on your T89. When you put in negative 2, you get undefined. So with that hole there, that means it's not continuous over this whole open interval. There's a discontinuity at x equals negative 2. And D, someone's defined something in pieces here, 2 lines. But the 2 lines don't quite connect. So we have a discontinuity here. Even though at x equals 0 it's defined to be negative 4, and at x equals 0, it makes this sudden jump up there. So that's discontinuous there. Now we have different kinds of discontinuities. It's a removable discontinuity if you can fix it. If I put a dot in, let's try that. See how we can fix this discontinuity by just filling it in. If we can redefine the function at that point with just one other point, that's fine. And we can fix this by saying, oh, let's move this up here. But there's no fixing this gap, because to fill it, I would have to put in this big vertical segment. And then it would flunk the vertical line test. So we call this a non-removable discontinuity. Same thing we saw over here. This is a non-removable discontinuity. So that's the difference between removable versus non-removable discontinuities. Okay. Now, let's discuss the continuity of each of these. With y equals 1 over x, we end up with a vertical asymptote at x equals 0, so that's a discontinuity. And it's non-removable, because there's no way you can connect up these two very disparate parts of the hyperbola here. This is going way down to negative infinity, this is going way up to positive infinity. So that's non-removable. This test continuity, we see this a lot. It basically boils down to x plus 1, a line, but it's got that hole at 1, 2. That's a removable discontinuity. We could patch it with just one single point. Here, it's continuous all the time. This person has managed to put together these pieces so that they agree at 0. 0 goes to 1. Here, k of x equals x squared, that's always continuous. No discontinuities there. And so this brings us to the discussion of the whole idea of directional limits. This special notation here, and let's really blow this up here. Oh, that didn't work out well at all. Let me just cut that out. This notation here is the limit as x goes to c from the right. We put a little positive sign after the thing we're approaching to indicate that we're going to approach c from numbers greater than c, like in the diagram here. And this notation, the limit as x approaches c negative, means not actually negative c, but as you approach c from the left, from values to the left of c, less than c. So the idea is we're going to want the directional limits to degree to actually have a true limit there. Now here's an example of one-sided limit. Find the limit as you approach this function, square root of 4 minus x squared, as x approaches negative 2 from the right. So as you approach negative 2 from the right, the values are getting closer and closer and closer to 0, the y values. The x values are getting closer and closer to negative 2, but the y values are getting closer and closer and closer to 0. Here's the greatest integer function. We've seen this stair step before with these little steps. With the left end is closed and the right end is open. Now what happens as x approaches 0 from the left and from the right? Well, as we approach 0 from the right, we're getting closer and closer to 0. But as we approach 0 from the left, the y values are staying at negative 1. So let's jot that down. The limit as x approaches 0 from the right of this greatest integer function, that's this direction like this, that's equal to 0. But the limit as x approaches 0 from the left of the greatest integer function of x, that's this idea. The x values are getting closer and closer, and the y values stay at negative 1. Now, because these directional limits don't agree, we say the limit as x approaches 0, then, of this greatest integer function does not exist. The directional limits have to agree. And that's what we talk about here. For the limit to exist, the limit as x approaches c from the left and the limit as x approaches c from the right of f(x) have to equal the same thing, have to equal the limit. So, discuss the continuity of this piecewise function, defined as x plus 2 when x is less than or equal to negative 1, defined as x squared minus 1 with x greater than negative 1. Well, let's take a look. The limit as x approaches negative 1 of f of x, that means we're approach negative 1, let's say from the left first. We're going to approach these things, and we put it into the left formula, and you get 1. But if we look at the limit as x approaches negative 1 from the right of f of x, now we're going to use the formula for points greater than negative 1, so that actually makes 0. as we come in from the right, it's getting closer and closer and closer to that point, which is a y-coordinate of 0. So the limit doesn't exist there. The function is defined there, but the limit does not equal the value of the function. So basically this is discontinuous at x equals -1. Continuous everywhere else, but they just didn't put the pieces together right. Now, continuity in a closed interval means you can just do the directional limits on the end here. So we don't have to have the limit as x approaches a from the left here. Here we can just say, does the limit as x approaches a from the right, is that getting closer to the value of a? Yes, it is. And here on this other endpoint, the limit as x approaches b from the left, is that equal to f of b? Yes. So that's how you can have continuity on a closed interval. Just like this semicircle is continuous on this closed interval from -1 to 1. Now the intermediate value theorem is very tricky. And it's the first of our big theorems in calculus where you have to be careful about the conditions for the theorem and also understand what the theorem is implying. It's called the intermediate value theorem because it's saying if you've got a value between two values, like k here is between these two values, and you've got a continuous function connecting points over this interval, then you've got to be able to reach this value k at some point. Now look at the exception over here. In this case, k is between f of a and f of b, but because the function isn't continuous, we never do attain the value of k there. Now, the intermediate value theorem is an existence theorem. It tells you there must be a point. It doesn't tell you where it is, but it proves that there must be some value of c in this interval to make f of c equal to k. So note the conditions. F has got to be continuous on the closed interval. F of a cannot equal f of b. And k has to be a value somewhere between f of a and f of b. The conclusion is that you should be able to find a c in the interval from a to b, some x value c in between these values of a and b, such that f of c equals k. And this is often used to show that you have roots between two things, because let's check out the conditions. Do we have the conditions for the intermediate value theorem here? First, f is continuous. On this closed interval from 0 to 1. Yeah, it's a cubic. It's a polynomial function. It's everywhere continuous. Now, what we have to do is look at the value. We want to show that as a 0. A 0 means that f of x is equal to 0. So our k is equal to 0. We have to show that k is an intermediate value between f of a and f of b. So we have to look at f of 0, and that's equal to -1. We have to look at f of 1, and that's equal to 2. 0 is between -1 and 2. So those are the conditions. It's continuous. F of a is not equal to f of b, and our value k is between f of a and f of b. So therefore, f is continuous on 0, and we've got all the conditions here. So therefore, there is a c in this interval from 0 to 1 such that f of c will equal k. In this case, f of c equals 0. Well, that's all the examples. And if you want to start the website, go ahead. But I'm going to go ahead and do a few more examples from some of these homework problems here. Let's look at this one, number C. It's another example of practicing directional limits. The limit as x goes to c from the right. So in this case, c equals -1. So as we approach from the right, that's going to follow the points along like this. And as the x-coordinates get closer and closer to -1 from the right, the y-coordinates are getting closer to 0. As we approach c from the left, now we're going to follow along this way. As the x-coordinates get closer to -1, the y-coordinates are getting closer to 2. Conclusion? The limit as x goes to c of f of x does not exist. The directional limits don't agree. So there's no limit here. Now, I could ask you part D, what is f of c? F of c is equal to 0, because we've got the closed dot there. But that's the value of the function at c. The limit as x approaches c does not exist. So f is definitely discontinuous, at x equals c in this case. Discontinuous. Okay, let's try some more. Here, I pulled 16 out of here. The limit as x goes to 2 of f of x, where f of x equals, in this piecewise function here. So, let's look at the different parts. If we approach 2 from the right, let's make that red, from the right, that means we're going to use values of x greater than 2. So we're going to use this formula. So let's put 2 in a synthetic division, synthetic substitution, see what we get. -1, -2, 2, 4, 2. So in this case, I'm getting the directional limit to equal 2. Now if we come from the other direction, though, if we approach 2 from the left, so I'm going to put a negative sign here, that means I'm going to take values of x less than 2, so I'm going to use this formula. Now I put 2 into 1, -4, 6, 1, 2, -2, -4, 2. Well, that equals 2. So, therefore, what do we get for our limit? The limit as x approaches 2 of f of x is equal to 2. The directional limits agree. And we can see this visually in our next page. I went ahead and plotted it on GeoGebra. And it almost looks like a cubic, but it's not. It's 2 half parabolas put together, and in just the right way to make it nice and continuous the whole way. I think I had one more in here. Oh yeah, the intermediate value theorem. Let's find that one. Oops, yeah, yeah, right here. I want to stop at this one to discuss the continuity of this function, x squared minus 24. Now, what I did in here is I noticed that they actually used the same function as over from a previous problem. But we're going to discuss the continuity of this over this interval from -1 to 2. Well, from -1 to 2 is focused on from here to here. And 2 is right where you have that vertical asymptote. -1 is defined in the function. You get -1/3. And it's defined all the way in here. We have no other discontinuities. We only have to really watch out for what makes division by 0 here, and that happens at 2 and -2. So this is continuous over the interval from -1 to 2, but not including it. So it's not the closed interval, because at 2 the function is undefined. So it's a semi-closed interval. From -1 is less than or equal to x is strictly less than 2. Here's the intermediate value theorem, restated again. And what you're supposed to do in this one is verify that the intermediate value theorem applies and find the value of c guaranteed by the theorem. So, it doesn't hurt to take a quick look at a picture of this. And when we look at a picture of it, we've got that vertical asymptote where we expected it, right? Here at x equals 1, you got a vertical asymptote. Just pop that in there. See that vertical asymptote there? Roughly at x equals 1. And we have some roots here at 0 and at -1. But we're only concerned with the interval from 5/2 to 4. And we're going to see if we can use the intermediate value theorem here. So first of all, is it continuous? Is f continuous on the interval from, in this case, 5/2 to 4? Well, let's take a look over here. 5/2 to 4. Well, yes. The discontinuity, the only discontinuity here is at the vertical asymptote of 1. So yes. So we've checked off that condition. And now we have to look at f of a and f of b. Let's look at f of 5/2. F of 5/2, you can plug it in the formula. You can also use your graphing calculator and see what you get there. When you put in 5/2, you get about 5.8. And f of 4 is equal to 6.67 or 6.7 or so. And sure enough, those are not equal. So we've satisfied the next condition. F of a cannot equal f of b. And now here's that third condition. K is a number in between those two. And we've been asked to do f of c equals 6. So in this case, with f of c equals 6, we're setting k equal to 6. And that is in between those two values. So we've satisfied all the conditions of the intermediate value theorem, so we can use the IVT. We've got all the conditions for it. Now the next part of the exercise, though, is to find the value that makes that happen. So, looking at the page here, we're going to have to figure out when does f of c equal 6. Well, in this case, f of x is given as this formula. So we have c squared plus c over c minus 1. What does that equal to 6? So c squared plus c equals 6 times c minus 1. C squared plus c equals 6c minus 6. And we get c squared minus 5c plus 6 equals 0. And this factors c minus 3, c minus 2. And so we get c minus 3 equals 0, or c minus 2 equals 0, c equals 3, or c equals 2. But don't lose sight of what the original question was asking. Find a c in the interval from 5/2 to 4. So apparently when we put in 6, we actually hit it here and over here at 3 and at 2. But only 3 is in the interval we're curious about, 5/2 to 4. So, but only c equals 3 is in the interval from 5/2 to 4. So there's your value of c satisfied by the theorem. And that, friends, is it. Hopefully you've had a few extra examples then. See you in class.